Okay, so if you've spent any time coding in Python, you've probably run into this, right? That weird type error with dictionaries, maybe?
Oh yeah, or that moment when your code seems fine on a small test, but then you throw real data at it and it just crawls.
Exactly. Well, today we're diving deep into why that happens.
We've pulled together some great sources looking at, the top 10 common mistakes people make, but also digging into the why, the Python data model itself.
Right, things like object identity, mutability, how data structures actually work under the hood, and how that affects performance.
Our goal isn't just to list errors. It's about understanding why they're errors in the first place.
Getting past treating them like typos and seeing them as, well, consequences of how Python is built.
hmm
Yeah.
Because once you grasp things like hashing or time complexity, you don't just fix bugs. You start writing code that's naturally faster, more robust,
Mm.
more Pythonic, really.
Okay, so let's start right at the core, because almost every Python puzzle seems to trace back to what an object actually is in Python.
That's a good place to start. Yeah, the sources really emphasize three core properties for every object.
Okay, what are they?
First, there's its identity. Think of it like its memory address.
Mm?
It's unique and never changes once the object's created.
Got it. Fixed address.
Then, its type, also fixed. Tells Python what kind of thing it is, a number, a string, a list, and what you can do with it.
And the third.
Its value. And this is the crucial part, because the value is what might or might not change. This leads us straight to mutability.
Right, mutability. This feels like the big dividing line in Python data types, doesn't it?
It really is. You have your immutable types, things like numbers, integers, floats, strings, and tuples. Once you create one, its value is set in stone.
So if I have x equal 5 and then I say x equals 6, I didn't change the 5.
Nope. Python essentially points the name x to a new object, the integer 6. The original 5 is still sitting there, unchanged, possibly waiting to be garbage collected if nothing else refers to it.
Yeah.
It guarantees the integrity of that original value.
Okay, that's immutability. But then there are the workhorses.
The mutable types. Your lists, dictionaries, and sets. These you can change in place. Add an item to a list, delete a key from a dictionary, you're modifying the original object.
And this flexibility is great, but it's also where the trouble often starts. Which brings us right to common mistake number 1. Trying to use something mutable, like a list, as a dictionary key.
Ah, yes. The infamous type error. Unhashable type list. Everyone hits this eventually.
So why does it happen? It seems like you should be able to use anything as a key.
Well, it goes back to how dictionaries achieve their speed. They're incredibly fast for lookups, right? That's because they don't just search through all the keys one by one.
They use hashing.
Exactly, hashing. It takes the key, let's say it's a string, and runs it through a special function to get a unique-ish numerical value, the hash code.
Hmm?
This hash code tells the dictionary, basically, where to store the associated value in memory.
Kind of like an index, but generated from the key itself, so it can jump straight to the data.
Precisely, like a super efficient filing system. But here's the catch. For this system to work, the hash value derived from a key must never change.
I see where this is going. If you use a list as a key,
And lists are mutable, meaning their contents can change.
then the hash value calculated from that list's contents could change too.
Correct. If you put something in the dictionary using a list 1, 2 as the key, and later that list somehow gets changed to 1, 3, its hash value would likely change. The dictionary would then have no reliable way to find the value you originally stored. The whole lookup mechanism breaks.
So the list is just too unstable to be a reliable key. Makes sense. What's the fix then?
Use an immutable sequence instead. The most common choice is a tuple.
Because tuples can't be changed after creation, their hash value will always be consistent.
Right, but there's a little gotcha here, the sources point out. Just using a tuple isn't always enough. The
Oh.
tuple itself needs to be hashable. That means everything inside the tuple must also be immutable. If you try to use a tuple that contains a list, like data 1, 2, 1, 2, that tuple is still unhashable.
Wow, okay. So the immutability needs to go all the way down. You can't have any mutable surprises hidden inside.
Exactly. For a tuple to work as a dictionary key, it must only contain other immutable types, numbers, strings, other tuples that follow the same rule, etc.
Okay, that clarifies the data structure side. Let's shift gears a bit. What about mistakes related to just calling functions or controlling the flow of the program, syntax and semantics?
Yeah, there are a few classic ones here, especially for people coming from other languages. One big semantic confusion is forgetting the parentheses when you mean to call a function.
Right. This ties into Python treating functions as first-class objects, doesn't it?
It does.
Right.
Let's say you have a function, def say hello dot return hello. if you then write message, say hello, without the parentheses.
What does message actually hold? Not the string hello, right?
Correct. It holds a reference to the say hello function object itself, its location in memory, essentially. You basically just created another name for the function.
So if you later try to print message or use it expecting the string hello, you'll get, oh, well, not hello, probably an error down the line or just the function's representation.
Exactly. You need message, say hello, with the parentheses, to actually execute the function and capture its return value. Big difference between referring to the function and running it.
Simple mistake, but deep implications. Now, speaking of simple mistakes, what about those really basic syntax errors?
Like forgetting the colon.
Yeah, the colon dot at the end of a def, if, for, or while statement. Simple, but it'll stop you cold.
True. Python's pretty good about giving you a clear syntax error for that one. It needs that colon to know you're about to start an indented block of code. It's non-negotiable.
And another one that trips up almost everyone starting out, trying to mush strings and numbers together. Mistake number 4.
Ah, yes. The type error you get from result plus 10.
Because Python is strongly typed, it won't automatically convert the number to a string for you in a concatenation.
Right. You can fix it by explicitly converting. Result plus string, 310.
That works. But is it the best way, the most Pythonic way?
Probably not anymore. This is where we lean towards readability in modern practices.
Yeah.
Using f-strings is generally much preferred.
Like result.
Exactly. For result, some variable, it handles the conversion automatically, the cleaner to read, often more efficient. It avoids the whole concatenation awkwardness.
Yeah.
That's the gold standard now.
Good tip. And one last fundamental confusion before we move on. Mistake number 5, mixing up and do it.
Oh, this one catches so many people, especially in conditional statements like if.
Because is is for assignment, right? It puts a value into a variable.
Correct. X equals 5 assigns 5 to x, whereas x is for comparison. It asks, are these two things equal in value, and returns true or false.
So if you accidentally write if x equals 5 instead of if x equals 5.
Checking if x equals 5. You're trying to assign 5 to x right there inside the if condition. In many cases, Python 3 actually catches this as a syntax error now, especially with the walrus operator, being the explicit way to do assignment within an expression. But conceptually, it's crucial for testing equality for assignment. Mixing them up leads to bugs or errors.
Okay, let's loop back, no pun intended, to mutable collections, particularly lists, because this is where performance gremlins often hide. Mistake number 7 is a big one. Modifying a list while you're iterating over it.
Yeah, this one's dangerous because it might not always crash. Sometimes it just gives you the wrong result silently.
How does that happen?
Imagine you have a list of numbers, say 1, 2, 3, 4, 5, and you're looping through it to remove all the even numbers.
Okay. So the loop starts at index 0 sees 1, fine. Index 1 sees 2. It's even, so you remove it.
Right. Now here's the problem. When you remove 2, the list immediately becomes 1, 3, 4, 5. The number 3 shifts from index 2 to index 1. The number 4 shifts from index 3 to index 2, and so on.
Ah. But the loop, it was planning to go to index 2 next, wasn't it?
Exactly. So the loop moves to index 2, but now index 2 holds the number 4. It completely skips over the number 3, which slid into the spot the loop just finished processing.
Whoa! So you'd end up with 1, 3, 5. You missed checking the 3 entirely.
Precisely. Or, depending on how you modify it, you could even run off the end of the shrinking list and get an index error. Modifying the list while iterating pulls the rug out from under the loop's feet.
Nasty bug. So what's the safe way?
The standard recommendation is to iterate over a copy of the list.
Like for item in my list.copy.
Exactly. Or use a slice for item in my list. This way, the loop is looking at an unchanging snapshot of the original list while you safely modify the actual my list inside the loop based on the items from the copy. Separation is key.
That makes sense. This whole mutability thing naturally leads to that big question. When should you use a list, and when should you prefer a tuple? We know tuples are immutable, which is good for data integrity.
Right, great for constants, configuration settings, things you know shouldn't change.
But what about performance? Is there a speed or memory reason to choose one over the other?
Yes, there often is, especially noticeable with large collections or tight loops. It comes down to memory overhead and how they're stored.
Okay.
Because a list might need to grow or shrink, Python has to allocate a bit of extra memory for it, just in case. And it needs mechanisms to handle resizing if you append lots of items. There's overhead involved in managing that potential flexibility.
But a tuple
is immutable. Its size is fixed forever once created. Python knows this, so it can store the tuple's contents in a single contiguous block of memory with no need for extra reserve space or resizing logic.
So tuples generally use less memory.
Typically, yes. And iterating over them can be slightly faster because the interpreter doesn't have to constantly consider the possibility of resizing. For static collections of data, tuples are often leaner and potentially quicker.
This feels like it's leading us into some deeper performance territory, especially for data science work. Let's talk about time complexity, that O versus $1.
Absolutely crucial for writing scalable code. All $1 means constant time.
Meaning the time it takes to do something doesn't depend on how much data you have.
Exactly. Whether your list has 10 items or 10 million, an O1 operation takes roughly the same amount of time.
Like getting an item from a list using its index. My list 500 takes the same time, regardless of whether the list is huge or tiny.
Precisely. Python can calculate the memory address directly from the index and jump right there. That's O1 at all.
Okay, so what's linear time?
That's linear time. Here, n represents the number of items in your data structure. An OR-on operation means the time it takes is directly proportional to the size of the data.
Like searching for a value in a list. If value in
In the worst case, Python might have to look at every single element in the list to find it or determine it's not there.
Yeah.
If you double the size of the list, you roughly double the maximum time the search might take.
Okay, I see the problem. If you're constantly searching large lists, your application's performance degrades as the data grows. That doesn't scale well.
Not at all. And this is where hash-based structures shine. Dictionaries and sets.
Because they use hashing for lookups, insertions, and deletions.
Right. On average, checking if an item is in a set, item in my set, or getting a value from a dictionary using its key, dig key, are overall operations. Constant time.
Wow, regardless of how big the set or dictionary gets.
Pretty much, assuming reasonably good hash distribution, which Python handles well internally. That overperformance is why sets are fantastic for things like removing duplicates or quickly checking for membership, and why dictionaries are the standard for fast lookups or counting frequencies.
So choosing a dictionary or set instead of a list for certain tasks can make a massive performance difference at scale.
Massive. It's often the single most important optimization you can make, choosing the right fundamental structure for the job based on the operations you perform most often.
All right, let's move into the final set of common mistakes. These seem more about writing code that's robust, professional, and maintainable. Mistake number 6, getting tripped up by variable scopes.
Yes, especially the difference between local and global scope, usually within functions.
So if I have a variable count equal O outside a function, and then inside the function I write count equal 5.
That assignment, by default, creates a new local variable named count that exists only inside that function. It completely hides, or shadows, the global count.
So changing the local count to 5 inside the function has absolutely no effect on the count outside the function, which is still 0.
Correct. The function acts like a separate namespace. If you really need the function to modify the global variable, you have to explicitly tell Python by using the global keyword inside the function, like global count.
But that's generally frowned upon, isn't it, relying on globals too much?
It is. It makes code harder to understand and debug. The much cleaner, more Pythonic approach is usually to pass the value into the function as a parameter, let the function work on it, perhaps returning a new value, and then handle the result outside the function. Avoid modifying globals directly if you can.
Makes sense. Okay, mistake number 8, sticking with verbose for loops when a list comprehension would be better.
This comes back to that Pythonic ideal code that's concise, readable, and efficient.
So instead of initializing an empty list, then doing a for loop, maybe an if check inside, and then dot append.
Right, that classic 4 or 5 lines of code just to, say, create a list of squares of positive numbers from another list.
You can often do it in one line with a list comprehension.
Exactly. Squares equals x squared for x in data if by 0. It reads almost like English. Squares equals x squared for each x in data if x is positive. It's clearer, less boilerplate.
And often faster, too.
Often, yes. Python can optimize the list creation behind the scenes more effectively than it can interpret the step-by-step append loop. For straightforward list transformations, comprehensions are usually the way to go.
Okay. Mistake number 9 feels like pure professionalism, not using doc strings.
Absolutely essential.
Yeah.
If anyone else ever needs to read your code, or even if you need to read it 6 months later, documentation is critical.
And doc strings are the standard way to do that in Python. Those triple quoted strings right after a def or class statement.
Yes. This function does X. It takes Y as input and returns Z. They explain the purpose, parameters return values. Tools can automatically extract these to generate documentation. It's just good practice. Code without doc strings is much harder to trust and use.
And the final one, mistake number 10, not handling potential errors or exceptions.
This is about writing robust code that doesn't just crash when something unexpected happens.
Like trying to divide by zero or open a file that doesn't exist.
Exactly. If you don't anticipate these possibilities and wrap the risky code in a try, except block, your program will just halt with an ugly error message. Bad user experience.
So the key is try the risky operation and accept the specific error you anticipate.
Specificity is really important here. You can do a broad exception, but it's generally bad practice because it can hide bugs you didn't expect.
So it's better to catch just zero division error or file not founder.
Yes. Catch the specific exceptions you know how to handle gracefully. Log the error, provide a default value, inform the user whatever makes sense. Let unexpected errors propagate so you know about them, but handle the ones you can predict. That makes your program much more resilient.
So looking back at everything we've covered, from those tricky dictionary key errors and iteration bugs all the way to scope and exception handling, there's a real thread connecting them, isn't there?
Definitely. So many of these common mistakes boil down to not fully appreciating the core properties of Python's objects, especially mutability and the inherent performance characteristics of different data structures.
That mutability concept seems particularly key. It gives you flexibility but comes with strings attached regarding iteration, hashing.
And performance. That overhead for lists versus the leanness of tuples is a trade-off you constantly need to evaluate.
It really highlights that the difference between just getting a script to run and building something efficient and scalable often comes down to picking the right tool for the job, the right data structure, not just defaulting to a list for everything.
Absolutely. Which leads to maybe a final thought for you to take away, something to mull over next time you start coding.
Okay.
When you reach for a data structure, actively challenge the assumption that list is always the starting point. Ask yourself, is this data fundamentally fixed or will it need to change?
Right. Immutable or mutable?
And then, crucially, what operations will I be performing most often? Am I mostly going to be accessing items by their numerical position? Or am I going to be constantly searching for items, checking if something exists in the collection?
Because if it's searching or membership testing,
Your mind should immediately jump towards sets or dictionaries, leveraging that potential owner constant time lookup speed. If you need fast indexed access, a list or tuple might be fine. But consciously thinking about the time complexity of your main operations, that's the shift in thinking that really takes your Python code from just working to being genuinely high performing.